examples out of yesterday's stuff. I talked to you. I found my rational root theorem proof. Okay. On Monday we will go through this, but you can see that the algebraic proof of the P over Q is not a real nice, clean-looking thing, right? Kind of messy looking. The one nice thing is that you know all the algebra that's being done there. If you understand division, you're good to go. Division is solving equations. That's all this is, okay? But this, and this is what I would have liked to have known, maybe had a little bit of insight into when I got into college and I'm taking an algebra class. This was the algebra that we did, okay? Because this is the algebra that solves every single polynomial or factors every single polynomial, okay? When we do the algebra that we're working on, I might get the exact answer for this one, okay? But that only tells me that I'm going to be proficient in that one. I might get another one with different coefficients that I'm not as successful with. I might get another one with different amount of terms in it that I'm not as successful with, okay? But if I can solve the generic polynomial, like we're doing here, if I can factor the generic polynomial, then I display or I demonstrate that I can factor any polynomial, okay? So that's kind of where some of your college classes might differ a little bit from what you've experienced at the high school level. So what you're going to see here, and there are some guidelines for finding rational zeros or an outline for this. First thing you're going to do is list possible zeros. Now the key word there is possible. Okay, you're gonna make a list of terms that not all of them are zeros, but inside that list, if this thing does cross the x-axis at a rational number, it is in that list created here in number 1. Okay, so we're going to list all the possible rational zeros. We'll talk about how we did that. The theorem from yesterday talks about how we do that, that P over Q thing. Okay, step 2 says then you're going to systematically choose values out of that list and do synthetic division on your polynomial with that value. And you're going to look at the remainder. The remainder is going to be key to us. We want our remainder to be what number? 0. If the remainder is 0, that's fantastic, because then that P over Q value that you just chose is a 0 of the function, meaning it is the next intercept, meaning then you know one of your factors of your polynomial. Okay? And you keep then repeating that process, choosing P over Q's and doing synthetic division until you completely factor your original polynomial. Okay? You find all the zeros. Okay? Now, what stinks about this is that you could potentially, yesterday we looked at this one here, right, with this 24, and we just wrote down all the P over Q's, and we came up with those 8, but they're plus or minus, so there's actually 16 there, right? How many zeros does that polynomial really have? 3. Those 3 are all in that list of 16, okay? But what could potentially happen is that we, in that list of 16, we could really try 13 P over Q values and fail in determining that all 13 of those are not zeros. Does that make sense? And then the 14th one would be a 0, and then the 15th and the 16th would be 0. So you would have a lot of synthetic division that basically led you to things that were not zeros. Okay? Some questions, it might be the first 3 P over Q's that you find to be your zeros. Some questions you might do, 3 or 4 synthetic divisions before you start to find one. Okay? What is also important is that we can have double roots, we can have triple roots, we can have quadruple roots. So just because, 2 in that situation would have given me a 0 doesn't mean that 2 won't give me another 0, right? Does that make sense? So when you get a remainder of 0 for one particular value, P over Q, through the synthetic division, you need to try that one again because it might give you a double root. If it gives you a double root, you got to try it again because it might give you a triple root. Does that make sense? So it is a technique that gets us all of our zeros, but it can be a tedious process. Okay, What really creates issue is when our constant term is very composite. Okay, the bigger it is, the more composite it is, meaning the more factors it has. Okay, I like it when this number is odd, and I really like it when this number here is prime. Okay, on a test or a quiz, I'm not going to make that number 96. Okay, I'm not going to make it 960. I'm not going to make it really big, because if it's really big, it's likely to have more composite factors. Does that make sense? Or be more composite than other factors or other values. 6 only has 4 factors. Okay, so I'll try to keep things kind of in that ballpark, so you can demonstrate that you know what's going on, but we're not wasting our time writing a list of possible P over Qs that's 15, 30 terms long. Okay, so first thing you're going to do in this process is that you're going to look at that term right there, and you're going to find the factors of it. What are the factors of 6? 1, 2, 3, and 6, right? So those are the terms that we call P. And they're going to be plus or minus. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay, so then the next thing is that you're going to look at the first term, your leading term. Okay, and you're going to find its factors. Okay, how many factors do you have there? 2, 1 and 2, right? So Q is what we call those, and it's going to be plus or minus 1 and plus or minus 2. All right. The next thing you do is that you have to determine what P over Q looks like. Okay, so you have to determine a list P over Q. All right, here is where a lot of people make mistakes because they will forget to deal with. They'll do this. They'll use P to be 1, and then they'll use P to be 2, and then they'll go P to be 6, and they skipped P being 3, and they lose ultimately 4 possible zeros. Okay, so my suggestion to you is be very systematic about the way you do this. Okay, so you're going to take the P value, the first P value, and you're going to write it as the numerator with those 2 Q values. So I'm going to say plus or minus 1 over the Q value of 1, and I'm going to say plus or minus 1 over the Q value of 2. Is that okay? Okay. Now, you only need 1 plus or minus with each of these, just because of the way a plus or minus numerator and a plus or minus denominator work out. You're still only going to get ever 2 results, plus or minus 1, plus or minus 1/2 in this case. So now you're going to do the same thing with the next P value. So you go plus or minus 2 over the Q value of 1, and plus or minus 2 over the Q value of 2. Do that again with 3 as the P value, plus or minus 3 over 1, plus or minus 3 over 2. And then finally, do it with 6, plus or minus 6 over 1, plus or minus 6 over 2. Is that okay with everybody? All right. So fundamental counting principle. Remember that? Remember Susie having 2 pairs of shoes, 3 pairs of pants, and 4 tops? How many outfits can she make? Okay. You took 2 times 3 times 4, right? Okay. You knew how many outfits you could have. P, there's 4 things there, right? Q, there's 2 things there, right? So there should be 8 total when we do P over Q. I always look at that and think about that because that could then help me realize, did I miss any P over Qs just through my process. Also, it kind of indicates that, well, the more factors that we have, so let's say this thing had like 8 factors, and let's say this thing had 8 factors. How many P over Qs would we have? 64, but they're becoming plus or minus, so there's 128 different possible zeros. Does that make sense? And that can be messy. Now, You're also going to say, well, there's some redundancy here. So when I do have maybe 128, just like here, we've got 16. But would you guys agree that this one here is redundant? 2 over 2 is already this one here, right? So you can cancel those out. Here's another one, 6 over 2. That's 3. You can cancel those out. So you don't strictly have basically 2 times your fundamental counting principle, but it's pretty close usually. Okay? Is that all right, everybody? Okay? So once you have that list, and some of your questions, your homework, are just going to ask you for that list. Okay? But now we're actually going to use that list. So we're going to go to the synthetic division process, which we're going to take our coefficients, so 2, 1, negative 13, and 6. And we're going to try one of those P over Q values. Just make sure you know which one you're trying, which ones that you've tried, so you don't accidentally skip one, miss one, or do one that has already given you a remainder that is not 0, and then you try that one again for some reason. Okay? So just be organized. My suggestion as we're doing this, the row of synthetic division that is going to be your remainder row, if you're using a pencil, do not push real hard. Just lightly sketch. Okay? If you're using a pen, you can't do that. But what's going to happen is that you're going to find out that the synthetic division doesn't always work. So let's try 1 real quick. If I try 1, bring my 2 down, I get 2, right? Synthetic division says that's going to be a 2. That's a 3. There's a 3. Negative 10. Negative 10. Negative 4, right? Okay? So that tells me 1 did not work. 1 is not a 0. So now I either have to start over again, so I have to write 2, 1, negative 13, and 6 again, create the whole synthetic division box again, okay? Or, if I've written lightly, I can just quickly erase that stuff and then try negative 1. Does that make sense? Okay, so I tried 1, now I'm going to try negative 1. Bring down my 2, gives me negative 2, gives me negative 1, gives me 1, negative 12, 12, 18. Is that a 0? Nope. So I keep going. So I tried 1, tried negative 1. They don't work. Okay. Maybe I try 1/2. Bring my 2 down. Gives me 1. Gives me 2. Gives me 1. So negative 12. Negative 6. I get my 0, right? Okay. So what's that tell me? Okay, so 1/2 works. So x minus 1/2 ends up being a 0, correct? Now, I could legitimately have done this and not realized a 0 all the way to maybe that last one. So you have a lot of these that didn't show me a 0, right? And a lot of work that may seem futile to us. Okay? It is what it is. If this was x to the third, this is just something to pay attention to. Because I would obviously have to try 1/2 again, because it could be a double root. Okay? And I could keep going and keep going through this list and trying synthetic division with this remaining 2 to negative 12. But there's a quicker way. So once you open the door to a quicker way, use that quicker way. So right now, this remaining row here states 2x squared plus 2x minus 12, right? And we're running out of time, but we'll do this on Monday. We'll finish that off using our quadratic factoring techniques, okay? And if that quadratic crosses the x-axis, okay, which I believe it does, then it will cross the x-axis at numbers that are inside that list P over Q. Does that make sense, everybody? Okay. Let me rephrase that. If it crosses that x-axis, it will. If they're rational numbers, it will be in that list. Okay. It can cross the x-axis at irrational numbers that have radicals in them, right? But we'll also be able to find those because we know how to use the quadratic formula. Okay. So that's key with that. Yes. So however large your degree is, so if our degree is 4, we would have to do synthetic division and find 2 zeros using synthetic division before we get down to a quadratic. If it was a 5th degree, we would have to go 3 times with synthetic division to get down to a quadratic. So the advent of technology allows us to maybe shortcut this a little bit. Descartes' rule of sign and the lower and upper bound theorem that we'll talk about next week also allows us to cut that list down a little bit. See ya. Have a good weekend.